Astronomers have discovered the nearest known black hole, Gaia BH1, which is part of a highly unusual binary system. In this system, a Sun-like star orbits a black hole with 10 times the mass of the Sun. The discovery challenges existing models of star and binary system evolution, as neither the common envelope model nor other theories can fully explain how the black hole could bind the star to itself without destroying it. This phenomenon once again challenges old principles of astrophysics and suggests that there are still many undiscovered phenomena in the universe. A binary system typically consists of two massive celestial bodies, such as stars, planets, or black holes, bound together by their mutual gravitation. The newly discovered Gaia BH1 system initially appears to be a normal binary system, but closer examination reveals puzzling facts that have left scientists at a loss for an explanation. Black holes of this size are usually connected to their stars in very narrow orbits. However, the star orbiting this black hole moves in a wide and highly elliptical orbit, making the duo impossible to explain with existing theories. The Gaia BH1 system is located about 1,500 light-years from Earth and was discovered by the Gaia mission, which has been measuring the positions, movements, and brightnesses of over 1 billion stars in the Milky Way since 2013. The aim of Gaia is to create a highly precise 3D map of the galaxy, providing insights into the structure, origin, and development of the Milky Way. In addition to general mapping, Gaia's search algorithms filter out unusual phenomena from the data sets, which is how the binary system caught their attention. The black hole in the Gaia BH1 system is most likely a stellar mass black hole with 10 times the mass of the Sun. Its companion star is a G-type main sequence star, similar to our Sun, with a surface temperature of about 5,850 Kelvin. This star belongs to the lower middle range of the most luminous stars in the universe. Scientists are now puzzled over the forces that have bound these two objects together. It is striking that there is no mass transfer between the star and the black hole. The star is not giving off any measurable mass to the black hole, and the black hole has only gravitationally bound the star to itself to the extent that it does not harm the star. The Gaia mission made this spectacular discovery, highlighting the incredible capabilities of modern telescopes and observation satellites. In addition to NASA's James Webb Space Telescope, ESA's new Euclid Space Telescope is providing incredibly detailed images from the cosmos. The Gaia mission, a project of the European Space Agency, involves a satellite placed directly in space that scans our galaxy around the clock. Scientists are looking for regularities in the universe, but they are also searching for the unusual. Repeating structures allow researchers to derive laws and understand the blueprint of the universe. The unusual nature of Gaia BH1 could be the portal to a new dimension of knowledge. At first, Gaia BH1 was recognized as a typical binary system, with two massive objects bound by gravity sharing a common gravitational center and performing a cosmic dance. However, closer examination revealed that this was no ordinary dance. After identifying the companion star, it was initially unclear who the dance partner was. When the black hole was discovered, scientists' curiosity was aroused. Binary systems of stars and black holes are fascinating, as black holes normally devour matter, including stars. If they bind to stars without harming them, as in this case, there is usually a balanced relationship of forces. The black hole binds the star just enough to allow it to orbit, but the star is not attracted by the black hole's gravitational pull. This usually results in very specific structures, and scientists thought they understood the conditions under which such a dance is possible. However, Gaia BH1 has shown that there is still much to learn. The star orbits the black hole on an elliptical orbit with a high eccentricity of 0.45 and an orbital period of 185.6 days. This circumstance is not physically possible under known models, as the star should escape from the black hole when it is at the furthest point of its orbit, and the black hole should suck the star in when it approaches again. However, neither of these things happens. The star orbits the black hole repeatedly in a safe orbit, raising the question of what binds the two together if it is not any of the known physical forces. Initially, researchers suspected that one or several other objects, such as neutron stars or white dwarfs, might provide stability between the two. However, all model calculations have so far yielded no meaningful results, as a third or fourth partner would likely destabilize the system. The dance of the two remains a mystery, and researchers are seeking answers. The next step was to confirm whether the second dance partner was indeed a black hole. Specific oscillations in the orbit of the star, known as wobbles, clearly indicated the presence of a black hole. These wobbles are like an object's fingerprints, and the wobble of a neutron star looks very different from that of a black hole. Despite this confirmation, the questions remain unanswered. Gaia BH1 attracted the attention of scientists for another reason. The binary system was found in a very isolated location in space. Since no standard model of binary evolution can explain it, researchers speculate that there is an anomaly in this area of the universe. Gaia BH1 challenges the common envelope evolution model, which scientists have long relied on to explain binary systems with close orbits. The common envelope evolution model, abbreviated as CE, explains how a massive star, as the progenitor of a black hole, becomes a red giant and expands. A companion star then enters the outer layers of the red giant, creating a common envelope that surrounds both stars. Through friction and dynamic interactions, the system loses energy, and the orbit of the two objects narrows. The envelope is eventually ejected, leaving behind a close binary system. However, this model does not fully apply to Gaia BH1, as the orbit of the Sun-like star is much too wide to have been created by friction in a common envelope. Additionally, there is no evidence of mass transfer from the companion star to the black hole, which is often the case in close orbits. This leaves scientists at a loss for an explanation. Another hypothesis considered by scientists is the triple star hypothesis, which suggests that Gaia BH1 originally emerged from a triple star system that became dynamically unstable and disintegrated, leaving behind the present system. This model assumes that the system began with three stars, two massive stars in a close orbit around the inner binary and a lighter third star, likely the G-type star, orbiting the two in a wider orbit. The two massive stars in the inner system could have evolved faster than the outer star, exploding as supernovae and leaving behind either a black hole binary or a single black hole formed by a merger. This could explain why the companion star is so far away, as the G-type star did not have to enter a common envelope. However, such triple systems are purely speculative, as the preceding events cannot be reconstructed with certainty. Known triple star systems with massive stars and highly elliptical orbits are mostly unstable, which does not apply to Gaia BH1. Thus, the triple star hypothesis also fails to provide a sufficient explanation. It is a fact that our science still knows very little about black holes in binary systems. Black holes play a significant role in astronomy, as they can tell us a lot about the evolution of massive stars, the dynamics of binary star systems, and even the origin of gravitational waves. However, they are not always easy to detect and are difficult to study, depending on the properties of the system and the activity of the black hole. Researchers use electromagnetic radiation as a source of information, particularly in the case of active black holes that draw in matter from their companion stars, producing strong radiation, especially in the X-ray range. This radiation is generated when matter spirals into an accretion disk around the black hole and is heated by extreme gravity. Such active binary systems with black holes are called X-ray binaries. In contrast, dormant black holes, like the one in the Gaia BH1 system, show no active accretion and can only be identified by their gravitational effect on the companion star. Precise astrometric data, such as that from the Gaia mission, can analyze the orbits and motion of the visible star. However, the possibilities quickly reach their limits when it comes to black holes. If the mass of the invisible partner exceeds the critical limit of about 3 solar masses, it is likely to be a black hole. Researchers also use gravitational waves or the aforementioned wobbles to identify black holes in binary systems. Gravitational waves are produced when two compact objects, such as black holes, merge. Currently, two observatories on Earth, LIGO in the USA and Virgo in Italy, are capable of measuring such waves with the help of the finest sensors. Wobbles, on the other hand, are generated by the visible movement of a star caused by the gravitational force of an invisible companion, creating the typical wobbles. The discovery of Gaia BH1 has opened up new questions and challenges for astrophysicists, highlighting the complexity and mystery of black holes in binary systems. As scientists continue to study this unusual system, they hope to uncover new insights into the forces and dynamics that govern the universe.